Okay, so I'll quickly explain our hardware setup. So we have a box, and inside the box we have a heating element, and so this heating element is nothing but a lamp. So the heat output of this lamp can be controlled from my microcontroller via PWM. And then inside this box there's also a temperature sensor. So we have this temperature sensor LM35. So the temperature values are sent to my microcontroller. So this is our analog temperature value. And then the third thing which we have is we have a fan. So this fan can actually quickly blow air into my system. So this can act as a disturbance or a faster cooling method for my system. So the speed of this fan can be also controlled via PWM. So this is how my system is. So here if you see the job of my PWM controller is to maintain a constant temperature inside this box. So for example, if the user says I need to maintain 40 degrees Celsius, so the job of the PID controller is to use this lamp heating element as input. So the PWM to the lamp is the input of my plant, using which I can heat up the system, and so I need to change the PWM accordingly such that the temperature keeps getting maintained at 40 degrees. So to check the actual temperature, the value of the temperature is read from this LM35 sensor. So this is my feedback. And other than this, the fan is actually used as a disturbance for testing my PID loop under all conditions. So even if I turn on the fan at max speed, the temperature should be maintained at 40 degrees. So we can use this fan to check how well the PID is tuned. So this is my job. This is how the hardware is set up and what I need to do from my PID. So for the PID loop, we'll be using this Type-C PID equation as explained by Professor Sawant. So for this Type-C controller, I have already written it. I've already written this function for implementing the PID loop. So it's written in this PID discrete function. I'll explain this in a while. So first I have a short demonstration to show you guys. So I have created this function, this first function which implements this Type-C PID equation, and then secondly there's also a second function, the PID double function, which implements the normal time PID equation, the very basic equation which we normally use. So this is implemented using double variables. And if you see in my Type-C discrete equation, I used only integer variables in all parts of this function. So the demonstration is actually to show you how much more efficient integer arithmetic is as compared to double variables. So what I'm doing is I have these two functions, and here in my setup I just initiate serial. Then in my loop I am firstly I'm taking timestamps at every point in my code. So the first timestamp I take is t1. So t1 is actually taken from this function called micros. So micros is a Arduino inbuilt function which returns the time in microseconds since the beginning of program execution. So it always keeps running in the background. So I take my first timestamp from micros here, t1, then I execute my function, execute any line of code. In this case it's this PID discrete function, and then I take a second timestamp and so the difference of these two timestamps is actually the total time it takes to execute this function in microseconds. So let's try this out. I'll first try the PID double function. So if you see for the functions, I'm just passing a simple double variable which I have declared here. So it's set to a value of 500 in both cases. For the double function, it's a double variable, and for the integer function, it's an integer variable, and but the value is the same. So this is just to I'm not interested in seeing what my output of the PID is. I just want to know how much time it takes for one iteration of this PID function, right? So if I just upload this, I have a Arduino board connected to my computer. Yes, let's see. So what these values are is just the time in microseconds it takes for executing this PID double function. So it's about 40 to 48 microseconds, as you can see. So now if we see the same for the PID discrete function, so it's actually a much smaller value. If you can see, it's about 16 to 20 microseconds, right? So it's almost less than half the value of the original PID double function, right? So this is why, as Rao sir has previously explained, this is why it's important to use integer variables at every point in your code as much as possible. So what happens is internally, if you consider the Atmega 328, it does not have floating point support inherently. It doesn't have a hardware floating point operation support. So whenever you use a double or floating point variable, what happens is internally the microcontroller internally uses integer variables only. So for even a single double to double multiplication, you may, for example, use 4 or more than that integer variables internally. So what you're seeing here is just an abstraction to give you a abstract value of a double. So it's very computationally intensive to use double or float values. So instead, for my PID function for implementing this equation, I'm using only integer variables. So how am I doing that? So let me explain this function further. So if you see, I have uh, initially, if you see my function, I have 5 arguments. So let me open my whiteboard. So for any PID process, you will see for any PID block. So there are three main things. The first input is the set point. Set point is the value at which you want the PID to set the process variable to. And the second input is the process variable, or PV, which we call it. In our case, set point is the temperature at which the user sets the value to, for example 40 degrees, as I said earlier, and process variable is the actual analog value of temperature read from my LM35. So the job of the PID is to always try to make the process variable as close as possible to the set point. So PID always tries to increase or decrease the process variable and make it as close as possible to the set point. So for doing this, the PID has the output of the PID out. So in our case, this is the PWM for the lamp. So these are the three things. So there's a set point, process variable, and PID output. So one thing to keep in mind whenever you program any PID controller, always and always, you must ensure that all three of these variables have the same minimum and maximum range. So in our case, the range of set point is was 0 to 1023, process variable also goes from 0 to 1023, and PID output is also from 0 to 1023. So you must always ensure that all three of these variables use the same minimum and maximum range, right? So this is the ranges that we will be using, 0 to 1023. So if you see my PID function again, I have my set point as the input, then there's the process variable which I get from the LM35, and then there are the three gains. So KP, KI and KD. KPD means for discrete, so KP discrete, KI discrete and KD discrete. So, and it returns the same thing, so it will return the PID out value. So inside this you have the EK value. EK is my error in every kth instant. So what K means is basically whenever I have my PID running, it runs in iterations. So whenever I get a new value of LM35, I run my PID and I try to change the lamp PWM. So this process keeps on happening repeatedly. So there are different iterations of my PID. So for example, PID runs once, it's the first iteration, then it runs again, then again, and it keeps on running again and again. So whatever the iteration of my PID is, that is the value of K. So this K equal to 1, K equals to 2, K equals to 3, right? So in every iteration I calculate my error, so that's error at the kth instant. And so next, P term, I term and D term are my values from the PID equation. So here if you see, P term is the red part in the equation, I term is the blue part, and D term is the green part of the equation. Next we have PID out, which is the output of the PID. Next we have CK. So CK is basically UK in this equation here. So it's the output of the PID before it gets converted to the appropriate range. So what I mean by this is, if you take any PID controller, the job of the PID, as time changes, let's say this is my set point, I set it at a constant value. So as my process variable starts from here, so my PID tries to bring it as close as possible to the reference. So it has some curve like this, right? We see a typical PID curve. So now in this case, we always say this is the error, right? This is the error. In every instant we have a different value of error, and PID tries to correct it, make it smaller and smaller. So if you see, the value of error can be positive or negative. So here we say that the error is positive, and here we say that the error is negative. So what I am trying to say is the PID may sometimes want to increase my process variable, and sometimes it wants to decrease my process variable depending on how the error is. So if the value is actually greater than the reference, I want my PID to decrease the process variable, so it comes closer to the set point, right? So in order to do this, my PID output needs to have effect of both these polarities. So it should even be able to increase my process variable, and it should be able to decrease the process variable as well. So if you see any PID equation, it's always dual polarity, which means that the output can be either positive or negative, right? But if you see, I said earlier that my ranges of the PID for these three variables have to be same, so it has to be 0 to 1023 in this case. There's no negative value, right? So if we directly constrain the output of the PID to 0 to 1023, I lose the negative effect of the PID, right? So in order to avoid that, what I do is internally from my PID equation, from the set point and process variable, I plug these values into my PID equation, and I get a value UK, I get a value UK. So this UK value is actually the CK in my program. So this value of CK can be positive or negative. So I set my CK range actually between -512 to 511. So it can be either negative or positive, right? And then internally, after calculating my CK output, I then just add 512 to it and shift the range. So my PID output is actually CK plus 512. Right, so effectively the range becomes 0 to 1023. So this is what I do in order to get my PID action in both the positive and negative ranges, and also to maintain my range of the PID from 0 to 1023, right? So this is CK. CK is the PID equation output, which is UK in this case. And next we have PVK minus 1. This is PVK minus 1. This is PVK minus 2. So if you see the PID equation, what this means is, as I told you, we have different iterations of the PID, right? K equals to 1, K equals to 2, K equals to 3. Then if you have K equals to 4. So in the fourth iteration, let's say we are in the fourth iteration, then K equals to 4. So at this particular iteration, the value of process variable, this would be PVK, and the last value of the process variable would be PVK minus 1. This is PVK minus 1, and K equals to 2, at the value of PV at K equals to 2 would be PVK minus 2, right? So I have to always store this past values of the process variable, right? So these are the variables that I'm using. If you see my PID equation right here, uh, you'll see I have PVK, the present value of the process variable, then I have PVK minus 1, the last value of the process variable, and then I also have PVK minus 2, which is the last to last value of the process variable. So I am storing this two past values in this variable here, and as you can see, I have declared these variables as static. So making these static means that it won't get redeclared. So once a variable is static, even if the function exits, the value of this variable is retained in memory. It doesn't get destroyed. So if during my second iteration of PID discrete, this line won't be executed. The value of PVK minus 1 won't be 0. It won't be redeclared. Since it is static, the value will be restored from memory, right? So that is why I am declaring these as static, since I want the values to be stored. Next, I calculate the error. Error is just set point minus process variable. Then we have del PV. Del PV is just this value of this bracket right here. So this is del PV. PVK minus 1 is del PV. Del PV2 is just the value of this green bracket right here. Now if you see, there's a negative sign here, and in our PID equation we are using a positive sign. So what we have done is taken this negative sign inside the brackets, and so that is what we are calculating here. After this, we calculate the P part, I part, and D parts. So we calculate the red part, blue part, and the green part. So in this calculations, if you see, it's KP for P term, it's KP times del PV as it's here. Now one thing to note is the ranges of the values. So in any microcontroller, while programming, you need to keep in mind what the ranges of each of your variables are. So for example, if I declare an 8-bit integer, the values would go from -128 to 127, right? This is the value of 8-bit signed integer. If it's unsigned integer, then the values would be 0 to 255. You need to keep this in mind always while programming, because what happens in this case is I'm using 16-bit integers in all these calculations, right? So while multiplying to 16-bit integers, so KPD is also a 16-bit unsigned integer, and del PV is also a 16-bit unsigned integer, signed integer in fact. So while multiplying to 16-bit, so for 16-bit int, unsigned int, the value goes from 0 to 65535, and for unsigned int, for signed int, it would be something like minus 32 something something to plus 32 something something. So what happens is, if you multiply or make some large calculations with this integer values, so the value of the integer value in my variable may overflow, may exceed the range of the limit which you are using. So in such cases, for example, if you multiply two 16-bit integers in like we are doing it here, the value may go beyond 65535. So that's usually bad, because it then overflows to back to 0 or to a negative value, something like that. So in order to avoid that, what we are doing is, before multiplication we are typecasting this del PV variable to a 32-bit integer. So by typecasting, by doing this typecasting, the multiplication happens in 32-bit arithmetic. So the result is also in 32 bits. So the microcontroller ensures that the value is not overflowed, right? So we have a result from the multiplication, and then we just bit shifted by 12. So this bit shifting is just for division by 4096. So if you take any variable a and I want to divide it by 2, so this is equivalent to a bit shift by 1. Similarly, a by 4 is nothing but a bit shifted by 2. So likewise, when I want to divide by 4096, I can just bit shift by 12. And for a divided by 65536, I can bit shift by 16, because this 6553536 is nothing but 2 power 16. This is 2 power 14. So every time you bit shift one position, it's equivalent to a division by 2. So if you look at my KP here, I have defined it as an unsigned 16-bit integer, and I'm telling you key I'm not using any, I want to avoid using any double or floating point variables. I only want to use integers. But in any PID, if you are seen typical PID gain values, the value of KP is something like 0.8 or 1.2 or 2.3, something like that. It's in this range. And likewise, KI is typically 0.1 or 0.05 or something like that. KD is also a small value like 0.01 or something like that. So how do I represent this values? How do I represent these values in integer ranges, right? So what I do is, I actually represent this value multiplied by 4096 or 65535, and then I divide it back, right? So in my case, for KPD, if I want to set KPD to 1, I'll just pass KP as KPD is 4096. So KPD is 4096 is equivalent to saying KP is equal to 1. These two are equivalent. Why? Because after multiplying here, I am dividing by 4096. Right. So if KPD is 4096, then KP is KPD by 4096. Right. So the equivalent KP becomes 1 if it's 4096. Similarly for KI, since I want a much lesser value, I Ki and Kd are normally never greater than 1, but Kp can be greater than 1. So for Kp I am dividing by 4096, and for Ki and Kd I directly divide by 65535. Okay, so this division is just to bring this ranges to an effective floating point value. So if you see the equation, I'm calculating the red part, the blue part, and the green part. Now for the blue part and green part, you have to note that KID, which I'm using here, is actually this term, this whole term here, TS by Ti times Kp. And this KDD, which I'm using here, is actually this whole term, Kp Td by Ts. So you have to calculate these values accordingly by keeping this Ts, Td, and Ti values in mind, right? So I get my red part, blue part, and green part in these three variables, and then I just add them. I get Ck, which is Uk. So Uk or Ck is just the previous value of Ck. In this equation, it's Uk minus 1. So I get Ck is nothing but the previous value of Ck minus P term, there's a minus here, plus I term plus D term, since we took this minus sign inside. Next, as I told you, from the equation itself, there's no bound to what my value of PID could be. So it could be any large value or any large positive value or any large negative value. So I need to restrict the range. So as I told earlier, I am as I told earlier, I have to limit my output range. So I have to set Ck between the range -512 to 511. So this is what I'm doing here. And then finally PID output is nothing but Ck plus 512. And I return that, which should be in the range of 0 to 1023. And then I am also storing my past values for the next PID iteration. So PV becomes PVK minus 1 and PVK minus 1 becomes PVK minus 2. So this is my PID discrete function. And so this works. I have tested this function well in many of our projects. Then even then, if you want to use this PID double function, the normal PID double function which we have here, I'd suggest you go through this blog once, improving the beginner's PID. So this is actually a very nice blog which explains the small nuances which occur in programming PIDs. So it has several pages which goes in detail on what you should keep in mind while programming any PID. Yes, so after this we'll open the test code for our PID, right? So we want to implement this PID for our actual hardware, as I explained earlier, this lamp heating thing. Now so the first thing to note here is for your system is running at 5 volt currently. So first thing to note is, I told you I have my ranges for the PID is 0 to 1023, right? So whenever I'm sensing my LM35 analog value, so the analog, I'll be using the analog read function, right? And this returns values in the range of 0 to 255. So what I do is, so this is nothing for reading the LM35. I'm using analog read. So this is nothing but the process variable, right? So but the range is much smaller than what we want. So what we do is I directly multiply this by 4. So multiplying this by 4 gets it in the range of 0 to 1023. It's actually 1020, but yeah, so it's 256 multiplied by 4 is 1024. So it's just a small difference. So I just multiplied by 4 to get my analog read value in the range of 0 to 1023. So analog read times 4 at the LM35 pin is my process variable, right? And so for the LM35, there's one thing which you have to note, which is the temperature, the actual temperature in centigrades divided by analog read times 4. This value is a constant for the LM35. For the LM35, temperature in centigrades divided by analog read times 4 is a constant, which is 0.1219. I have written this here. So this is a constant. So for in my PID, for example, if the user has to set the temperature to 40 degrees, let's say, so temperature in C 40 degrees divided by 0.1219, this value, it comes out to around 328, I think. About 328, I'm not sure. So this is the value which is actually the set point to my PID. If I want my temperature to be 40 degrees, this would be the actual set point to my PID in the range of 0 to 1023, right? So for the user, I've made it easy. You can just directly input your set point in centigrades and it gets converted right here for the PID. So this is the first thing. Then secondly, you need to initialize all your pins. So according to the hardware, I've set the pin definitions. Then you have some global variables for storing the analog values from the sensors. There's a debug LED which is attached. Then there's a print time variable. I'll explain this in a bit. And next there are the PID gains. So I have defined both my double function and the discrete integer function. So I am setting gains for both these functions here. Then there's a PID temperature set point calculated from the user input, and then there's a PID output which is defaulted to 0. Next we have this function for analog read. So what happens is, for this just a simple software low pass filter. So what happens is, in any analog read, if you have tried it before, let's say you have a sensor and you are reading values from it repeatedly. So let's say the value revolves about 500, revolves around 500. So as time varies, you are getting different values, which vary slightly typically. So it could be 501 or 498 or something like that. You get some small disturbances in your reading always. And it may so happen that during runtime, sometimes because of voltage spikes or any kind of disturbance, there's a abnormal spike in the reading, right? So there's a sudden difference, like we are reading 500, 501, 498, then there might be a reading of 800, which is totally abnormal. It's false reading, and we don't want this false reading to affect the PID, so we want this to be ignored. So what we do is, we implement a low pass filter, since this is a high frequency spike. So for implementing this low pass filter, it's a simple equation. What we are doing is, the analog value I'll call this I'll use a simpler name. Let's say new value. So anytime I'm reading from the sensor, I get a new value, right? So this new value is, I take it always as 9/10 of the old value, which is the previous new value. So new value is the previous new value, 9/10 of the previous new value plus 1/10 of the red value. So this is the value which is getting read from the pin. So only 1/10 of it affects my new value. Right. So what happens is, oh, if there's ever a spike, only 10% of it gets affected, is actually affecting my analog read function. So if you just rearrange this equation, I'll get new value as old value plus zero point 0.1 times zero point 0.1 is 1 by 10 minus old value. So new value is just the value which actually gets read from the pin, right? So whenever I have a new value from my ADC, only 1/10 of it affects my actual reading, which gets returned. So in my function, I'm just taking my pin from which the value has to be read. So I read from that pin. This is the new value, and only 1/10 of it affects my actual value, which is read, which is used in my software. So I return this. Next, I have my double PID function. This is not actually used, it's just there for testing. After this, I have the discrete PID function, which I explained earlier. Yes, so now I have the setup of my function. I initialize serial, then I define all my pins as input or output, and then initially I am keeping my lamp as off and the fan is also off. So the motor actually stands for the fan, the cooling fan which we have in our hardware. After this, I'm setting my timer interrupt. So why do I need a timer interrupt? Normally, whenever you're writing any Arduino program, you have a setup function. Here you do all your initializations, right? And then you have a loop which keeps on running forever. And then in normally you put all your logic and calculations here. All your program logic and calculations come here, right? But this is actually not suitable for many of the many of the real-time applications, because what happens is, let's say I put my PID loop here. Then apart from my PID, I need to also read values from my ADC. I need to print some debug values for the user to see. So I may be reading some values. For example, I may be taking the set point as input from the user, so I have to read these values, right? So in any in this function, in this application also, I have some tasks to be done, right? So if PID is put along with these tasks, what happens is, if you see my PID equation, I have this term called TS. So TS is the sample time. So TS sample time is nothing but the difference in time between these different iterations of my PID. So between k equals to 1 to k equals to 2, the time difference is actually TS. So this is TS. So from my equation, since my PID equation is dependent on TS, it is desirable for us uh, to have simpler calculations. It is desirable for us to keep TS as a constant. If TS is a variable, then it's tedious for us to recalculate it again and again. So in our application, we try to keep TS as constant. But to keep TS constant, we need to ensure that PID function gets calculated at at equal intervals of time, right? So, but if we put the PID function in void loop, this the time difference between successive calls of PID is uncertain because of these other things which I'm doing in my void loop, right? So sometimes printing or reading from serial may take different times. For example, one iteration may take 10 milliseconds. In the next iteration, it may be 12 milliseconds, maybe 20 milliseconds. So this time for the execution of void loop is uncertain. So I can't put my PID loop in here because then TS is variable. So in order to maintain TS constant, what I do is I use timers. So in my timer ISR, I'm actually in my timer ISR, I'm setting the timer such that I get a timer interrupt every 10 milliseconds. So whenever I get a timer interrupt, it goes to this timer ISR. So this interrupt service routine, which gets called every 10 milliseconds. I have configured it to get called every 10 milliseconds. So inside this timer ISR, I'll be calling my PID function. And the other things which has to be done, like read ADC and then the print values, read values, these other non-time critical things can be put in void loop. But this PID function would always and always run every 10 milliseconds. The timer ISR ensures this. So even if I'm in the middle of execution of this function, whenever there's a timer interrupt, the code will stop at this particular point and then it'll come here. It'll execute my PID and then it'll go back. So this timer ISR ensures this. So so this will keep my TS constant. So I can eliminate, I don't need to write this in my TS in my function. I can assume that it is constant. So I configure my timer, then I have my void loop. So inside loop, as I said, I have to read ADC. So I'll be reading the analog value. This is the function I with the low pass filter I explained earlier. So I'm reading values from my LM35. I'm storing the present value to be used as the old value for my next read. Then for printing it uh, to the user, so the user actually needs to see what the current temperature is inside the box. So I need to print the values in centigrades. So I'm converting this red value to centigrades for the user to see. So I print this debug information, this temperature and the PID output every 1 second. So for printing every 1 second, I'm using this Millis technique. So this is just a small technique to avoid using delay. So normally whenever a beginner writes an Arduino code, you have in your loop, let's say I tell you you need to print a message every 1 second. So you will do something like serial.println hello, I need you to print hello every 1 second. So what a beginner would do is you would write a while loop serial.println hello, then you would use delay 1000 for 1 second. So this is what we do initially in our initial stages of learning Arduino. We use delay a lot. So but the problem with delay is that it's a waste of CPU cycles. So whenever delay is executed, the microcontroller is sitting idle for 1 second. It does nothing, and it can actually be very counterproductive in real-time applications to use delay. So instead, for example, in our application we need to print debug information every 1 second. Let's say we want to print the temperature. So if we use delay here, and then if we have a read ADC function before that, what would happen is my read ADC function would also be called every 1 second, which is very slow. So I need to ensure that my printing happens every 1 second, but my reading ADC is not affected because of this delay. So I have to avoid using any delay. So instead of using delay, I use this Millis technique. So the technique goes as follows. Whenever you print any debug information, I record the time of printing in this variable called print time. And so once you print it and you record the time, then in subsequent iterations of while loop, you would be constantly checking whether the current time minus the print time is greater than 1 second. If it's greater than 1 second, then you'll print it again. Right. So effectively, this if statement creates a delay in printing the debug information. Right. There's also a debug LED which is toggled every 1 second. So this XOR equals to 1 is for toggling the debug LED. So after this, we are reading values from the serial. This for taking user input. So in our system, we have a fan, and so we have a fan for introducing disturbance or cooling. So I may need to turn on or turn off the fan in between my program execution to see how the PID reacts. So the fan PWM actually varies from 0 to 255. So this value is actually taken as user input from the serial during program execution. And then second thing is the set point. So in order to change the set point, as of now, if we don't write this read thing, you'll have to re-upload your program again and again just to say change this set point. So we don't want that. We want to change the set point dynamically as the program is running. So in order to do that, we accept the set point as user input from the serial. Set point in centigrades. So whenever I have defined the format as the user would, in the serial terminal, the user can actually enter values for my fan PWM and set point by in this format. So it's fan PWM comma the set point, which could be 45 degrees. So this is the format which the user has to follow: fan PWM comma the set point in centigrades. So whenever you type this and send this to the Arduino, this this particular if statement gets true because you have characters in your serial stream. So you use serial.parseInt. So this parseInt will read my first value, which would be the duty cycle, Then the second call of parseInt would give me the temperature in set point. And so using these values, using the duty cycle, I change my PWM for the fan, and then using the set point, I change my PID set point according to the relation I explained earlier. Then I just print it for the user to know that yes, indeed, the values have been received, and we discard any extra characters. So this is what my while loop is doing. And then after this, outside of loop, I have my timer ISR. And so the timer ISR is only performing the PID computation. So inside the timer ISR, I have this PID function, which takes the set point, the analog read value times 4, and the KP, KI, and KD values. And it gives an output in PID output. So this PID output is actually in the range of 0 to 1023, and I divided by 4 to get my duty cycle. Uh, uh, Duty cycle, the range of 0 to 255, and this is actually the value which increases or decreases the intensity of the lamp, right? So duty cycle is PID output times 4, and this is just a small error checking thing. Then after this, I write duty cycle to my lamp pin, and I repeat this every 10 milliseconds because of the timer ISR. So this is the code for doing the PID testing on my hardware. Now we'll connect to, I'm using AnyDesk to connect to Rouser's laptop at his home, and the lamp and everything, all the hardware is connected to his laptop. So I have uploaded the same code here, and I'm seeing what's happening on the real-time system. So right now, if you see the serial monitor, it's reporting a temperature at about 35 degrees. So actually set the set point to 35 degrees. And if you see the PID output, it's varying to maintain the temperature to 35 degrees. So just to demonstrate, I'll change my set point to 40 degrees. Right. Right now I'm using these gains. If you can see here, these are the gains which I'm using. So I'm not actually using the D term, it's set to 0. I'm using KP and KI, KP and KI. So I can change my temperature set point at any point. So the first value is the fan PWM. So I'm setting it to 0. I don't want my fan to operate. Then the temperature set point, I'll set it to 40 degrees. So I can just send it. And then you can see fan PWM set to 0, temperature set to 40 degrees. So as soon as I set the temperature to 40 degrees, you see that the PID output starts increasing to make my temperature higher so that it reaches 40 degrees. Right. Now, one problem with this system which we have designed, this lamp and heater thing which I have designed, is that it's the natural response of the system is very slow. So it actually takes a very long time to heat up and cool the system. So even if I'm operating even if my PID output is maximum, if you see it's 1023, the lamp is at full brightness, even then the temperature actually uh, increases quite slowly than we want it to. So we have to wait a bit. It's increasing, then it will eventually settle down at 40 degrees. It slowly varies. There are some glitches in temperature always from the LM35. It's not particularly a precise temperature sensor.
You can also show the actual system, no? Camera se.
Uh, I can open the camera and show it. Actually, if I open the camera now, it starts lagging a lot.
No, that's okay. Just for at the end of the session, just show the actual system.
Okay, at the end of session, I'll show it. Yes. Yes, so once my temperature reaches to 40 degrees, you'll see the PID output slowly decreasing to a particular equilibrium value. Right, so PID action is happening. So I've actually kept this overnight as well, and then the temperature gets maintained constant to 40 degrees. Now, even if I turn on the fan, uh, if I turn on the fan to full speed and set point remains 40 degrees. Now, since my fan is blowing, you'll see once it starts cooling the system, the PID output has to actually fight for keeping it at 40 degrees. Now note one thing, in this particular gain values, the at every PID iteration, the change is quite small. For example, I'm going from 60 to 80, 80 to 90, then 100, then 100 to 200, 300, 400, 500, 600. So the changes are quite small, right? So if I want this PID output to react more dynamically, then I have to increase my KP and KI. So if I increase my KP and KI, what happens is there's a possibility of overshoots. So to reduce these overshoots, I introduce a D term back again, right? So this thing will keep happening. I'll change the gains here. So you'll see if I introduce the D term, even if I make it 1, in a present system, even if I make the D term 1, then the action is such that I can increase my KP and KI to a very large value. So from 2000, I directly take it to 50,000 and KD to KI to from 100 to 15,000, because the D term allows for a faster response to take place. So it's at 40 degrees only. I'll perhaps change it to something like 42. I'm not going to higher temperatures because it will take a much longer time for it to reach there. We'll have to keep waiting. So in this case, for this gains, you'll see my PID is able to increase and decrease quite fast. So from 200, I could go directly to 900, then to 700, then 800 to 500. So basically, the PID is able to react a lot more quicker. Right, since I introduced the KD term, the KP and KI terms could be set to a much higher value. So it'll settle down to about 42 degrees. Yes, so similarly for same gains, if you for just for seeing if you remove the KD term, you'll see that there's a lot of slow oscillations happening. The PID output will decrease and increase slowly and steadily. There's a lot of oscillations happening. I won't show it now because it takes a lot of time to actually see it since the system is okay. I'll move on to the last section of my explanation. So this is my PID action and how my code is set up. Now, if you ask me how I've set the gains here, how I decided that this should be the value of gain. So I've actually used the manual tuning method as Sawan explained. So from my own experience and from just testing out different values, I finally settled on this gains. So as Sawan explained, I first set KP, then I set KIKD to 0 initially. Then once I am getting some appropriate response, then I introduce a KI term. Then once the KI and KP term, the KP and KI terms almost brings the system to a good response in this case. You don't actually need a D term for this system, but for if you do introduce a D term, you get a much better response, right? For actually appreciating the value of the power of the D term, you need some fast reacting system. For example, you have done some projects on balance board, or for example, for the control system of a drone. In such cases, the D term and all the KPKI and the D terms are actually playing a big role in how they affect the dynamics of the system. So in this case, it's a quite a slow system, so it doesn't really matter much. So hence, right now I have used the manual tuning method. So, so the future work for some of you guys would be you could actually take this values from the system, take this temperature and PID output values from the system over time, make a data log out of this, and then take it over to MATLAB. As Sansar explained, you can import system data in MATLAB, and then you can do your PID tuning there. Right. So this could be a future work for some of you. You could actually find much better gain values for the system using MATLAB or some other mathematical operations. One thing is that. Then second thing is I think the hardware itself is quite slow. Then you can introduce a much powerful or a faster heater and see how then the gain value changes. One thing to be noted is the gain value also, the optimal gain value also changes depending on my set point at which I'm operating. So, for example, at 40 degrees, I have a particular set of gains which are optimal. Then for 80 degrees Celsius, for a practical system at 80 degrees Celsius, I would have a slightly different set of gains which are optimal, right? So you need to test these things out. And then the third thing is, as Rao sir explained, you can add some IoT to the system. So in the board itself, there's a option for adding a Wi-Fi module or something like that. And then instead of using AnyDesk or something like that, you can use some simple text-based server client architecture to actually modify your gain parameters and see the response of the system. Or you could create a GUI or something like that to further study this system. So we'll just open the camera and see
Srijal,
what.
may I interrupt?
Yes, sir.
Srijal, last time, I think a few days back, you have shown me some graphical tool to actually take this data to the GUI.
Yes,
So
there's
can
also
you
that
give
option.
them as a future work
Yes, 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 yes.
kind of thing?
So for the Arduino system, there's this software called. You can see my screen, right? So there's this software called processing. So this processing is actually a different language kind of thing, and they have adapted it for Arduino for giving it GUI capabilities. So in Arduino, if you normally see, you only have this serial monitor, or max to max, you have this serial plotter option, which if you see here, there's a serial plotter option. So this can also be used to plot values, but it's very limited in functionality because you can only plot a single variable, and then you can't really control the how the axis react. So this is limited in functionality. So to get full GUI capabilities, there's this software called processing, and using this, basically you have to install this processing software onto your system, and then there are some steps to be followed. It's explained well in a lot of tutorials, for examples, SparkFun tutorial. So it will explain you step by step how do you install processing, and how do you get your GUI graphics to get your GUI graphics working. So after once you do that, you can actually plot all your PID values, and you can see how the I don't see a good example. Yes. So it's something like this. You can actually plot all your set point and the PID output and everything, and you can actually see it in real time. So for doing this, you need to install a separate software. I've not done that right now. Uh, so yes, answer. Using this, you can add those graphical tools to your Arduino system. Yes, and I'm back to AnyDesk, and I'm connected to Rouse's laptop, and this is the hardware system which is actually present at his house right now. And so on the left, you'll see this green colored PCB which Rouser has designed. So it has a Atmega 328P, which is the same controller as an Arduino Uno. And what we were seeing earlier in the serial monitor is values from this controller itself. So it's connected to the laptop, and I'm controlling the laptop. So I can upload code from directly from here, and then I can also see how it reacts. So it's lagging a lot right now. Don't know, maybe the internet connection is poor. But if it's running smoothly, it was running smoothly earlier. You can see the system dynamically reacting. For example, if I turn the fan to max speed, you can see it rotating here, and then even the lamp glowing can be seen through these holes. And so that's the hardware system which we are working with.